There we go. Yeah. I am just looking for one setting in my. All right, I'm sharing my other screen with you now. Let me know when you can see my screen there. So here is my Cisco packet tracer. And I gotta sign that in. Just a minute, let me enter my password. All right. And there you go. I hope you can see my camera now. You can see my screen now. And the section that we are going to discuss in this is routing information protocol. So there are different methods that you can actually implement routing information protocol, and this section actually comes in when we discuss about like dynamic routing. So there are two variants, right? You have a static routing and you have a dynamic routing. When we look into static routing, then you can say that there are different types in static routing that we have implemented so far, but we also have seen a type of dynamic routing. So you have static routing, in which we saw normal static routing, then we saw default static routing, and then we saw floating static, right? But if we talk about dynamic routing, then there are multiple protocol that comes under dynamic routing. So first of all, you have routing information protocol. Then you have Eigrp, which is enhanced interior gateway routing protocol. And then you have OSPF. So when you have these routing protocols, then there are other routing protocols as well, like BGP, like ISIS, right? You might have heard about them. And there is categorization that is actually done for all of these routing protocols, like RIP, it's called as distance vector routing protocol. AIGRP stands for AIGRP comes under Advanced Distance Vector Routing Protocol, and OSPF comes under Link State Routing Protocol. Right? We'll be discussing about each and every protocol that we have here. But what we are going to discuss in this particular session is routing information protocol. So when we talk about routing information protocol again, then it clearly works more of how you can actually exchange routes. For example, if you have a router 1, then you have a router 2. And this router 1 has, I would say, certain connectivity of local area network like this. Okay, and then you have your network like 192.168.1.0 on here, you have 192.168.2.0 there, and you have 192.168.3.0 there. So when I look forward in order to send traffic from this network to this network, then in static routing, you actually need to add the indirectly connected network. We saw that how 1.0 will be the directly connected network to R1 and 3.0 will be the directly connected network to R1. Then we implemented a way that 2.0 actually needs to be added into the static route of R1, right? And 1.0 needs to be added into the static route of R2. But this is kind of not that scalable solution, because if you have multiple static routes, then in that particular case, you probably would have, yeah, you probably would have seen something that if you have around 10 or 15 routers, or even more, 20, 30 or 40 or 50 routers in your environment, then in that case, adding all these routes or adding all the indirectly connected network route in your routing table is not going to be a scalable solution. So what do we do in dynamic routing, and how does dynamic routing actually work? Usually, when you have a router here, and then if you have a router there, then assume that your R1 actually knows about 4 routes. Your R1 knows about 1.0, your R1 knows about 2.0, 3.0 and 4.0. And your R2 knows about around 5.0, 6.0, 7.0 and 8.0. These are basically the directly connected networks to your routers. So in dynamic routing, you are not going to add the indirectly connected routes to your routing. What you are going to do over here is you are going to add you are going to advertise the directly connected routes to the neighbors or to the routers that are present into the topology. Make sense? And how that's going to happen? It's basically going to happen in a way that R1 is going to send routing update, and in that routing update, it will contain all the details of the directly connected network that it has. And R2 is also going to do the same thing. R2 is going to initiate a transfer, which will also be called as a routing update. And in that routing update, it will contain all the routes that the router knows about. This is how we actually think about when we give it a thought that what is dynamic routing. Do you understand what I'm trying to say here? The meaning of dynamic routing? Perfect. So when we actually talk about this dynamic routing, then RIP is one of the protocol that we discuss about, or you can say routing information protocol is one of the protocol that we call as distance vector protocol. Okay, and when we look about it, then you can say, let me just clear this from my display. Yep. So we are about to discuss how routing information protocol works. And in this routing information protocol, how it actually is going to work is you're going to have a router and you're going to have another router in your topology, and we are going to advertise the directly connected networks that are available there. But there are certain characteristics that you actually need to know, that how the communication is going to work over there in terms of routing information protocol. So first of all, when we talk about routing information protocol, the very first thing is it is open standard protocol, which means if you have a device that is connected of Cisco and if you have another device that is connected of Juniper, okay, then you can actually implement routing information protocol between them, and it's not a vendor proprietary protocol. You don't need to worry about which devices are you connecting, or does the are the vendors of those particular devices are same or not. Since this is an open standard protocol, you can implement routing information protocol in almost every device that is available there. Make sense? Then after that, you can say that when we actually give it a thought, the second, you can say, characteristics of your RIP is it is classless routing protocol. Okay, it is classless routing protocol. And what does this mean? It means that if you have a network that is created of /28, let's say, and then you have a /29 network here and a /30 network here. So you can actually advertise these /28 and /30 and /29 network inside the RIP, because RIP or routing information protocol had two versions. It had version 1 and version 2. Version 1 was only supporting classful routing, like you can say classful routing, which means you can only advertise your network if the networks are of /8, /16 and /24. You understand that? That was one of the limitations then. And if you talk about V2, then you can advertise almost every network that is available, be it /16, be it /18, be it /29, or be it /30, or almost any network. Okay, you don't need to really be worried about how you can actually do that. Just a minute, guys. Yeah, sorry about that. So, as I told you, that the second characteristics of our routing information protocol is you can actually uh, advertise your networks even if they are of classless nature, which means if the networks are made up of /28, /29, and not the default subnets, they are not following the default subnets. That's one of the second characteristics that you have. Then the third characteristics that you have here is what you can do with I can say routing information protocol is you can actually advertise your networks, or you can like advertise your networks based on the routing updates, which means that every 30 seconds your router can actually advertise a routing update, which means if you have a routing table that actually contains around 10 routes, then those 10 routes will be advertised on a multicast address every 30 seconds. Okay, and these advertisements are going to be made into that particular router, and then there the routers will get to know about those routes there. This is how it's going to work there. Makes sense. Now what we will do, we will try to create a network, and we will try to see how the advertisements are done and how the communication actually happens with the help of this routing information protocol, and see how it works. Okay, let me just clear this particular screen here, and then I'll demonstrate to you guys that how we can make this work. Just a minute. There you go. If you can see my screen now. So we are going to drag a couple of routers here. Let's say this PT router here and here. And then I am going to drag another router here and here, and then another over here. And then I'm going to connect them together like this. And we're going to have the common networks again. I'm going to have 192.168.1.0/24. Then I'm going to have 192.168.2.0/24 and 192.168.3.0/24. And after configuring the basic IP settings, what you can do is advertise your networks. But before that, it's going to be much easier than the static route that you did. So I can say no here, enable, configure terminal, then interface FA0/0, no shutdown, IP address 192.168.1.1 along with the subnet mask, and then you can say IPDSCP pool A network 192.168.1.0 along with the subnet mask, and default 192.168.1.1. Sounds good. Then you can take an exit and then configure the next interface, which is SE2/0, and say no shutdown and IP address 192.168.3.1 along with the subnet mask, and take an exit from there. You see, that's how you configure the two of the interfaces that you have, which is for FA0/0 and which is for SE2/0. So after that, you go ahead and go to the PCs and configure the IP addresses on them and requesting IP, and there you go. Then I'll go to the next PC and configure the IP address there as well. There you go. And then I can go on over here. CLI no enable conf interface FA0/0 no shutdown IP address 192.168.3. 2.1 and then IP DSCP pool B network 192.168.2.1 sorry, along with the subnet mask, and default 192.168.2.1, and take an exit. Interface SE2/0 again, no shutdown, and IP address 192.168.3.2 along with the subnet mask, and take an exit. You see that? That's the normal IP configuration that we have done, and your entire network is up and running. Correct? I can check the routing there as well. Yeah. So I can say over here, do show IP interface brief. There you go. FA0/0 is configured with 1.1, 2/0 is configured with 3.1. And then you can see here, do show IP interface brief and 2.1 and 3.2 there. Sounds good. So when I take an exit there, then you can actually also check the routing table, that my routing table doesn't really contain anything from 1.0. So in the static routing scenario, we kind of added the static route over there, right? But in the dynamic routing, we are not going to add any indirectly connected network into our router. So how do you advertise your route? Your route actually is advertised in a way that you open up a router and you can give this particular router a hostname R1. You can give the other router the hostname as R2 by going into conf hostname R2. Yeah. And then you create a routing RIP or RIP instance by saying router RIP version 2 and then network 192.168.1.0. You need to advertise your first directly connected network. Then you say network space 192.168.3.0. You advertise your second directly connected network. Make sense? And then after that, you go on to the other router. You can check the routing table that 2 and 3 are the directly connected networks. So you create router RIP instance by saying router RIP. Then you select version number 2 there. And then you say network space 192.168.2.0 and network space 192.168.3.0. You get that? And after you advertise both of these networks, then the router will send an advertisement of all the routes that this particular router knows about and all the routes that the other network knows about, okay, into one another. Make sense? Then if I go on to the first router and if I check show or do show IP route, then you can see that there is a new update there in router rep. That says 192.168.2.0, which is highlighted with R, and R stands for RIP. Okay, so this particular route has been learned via 192.168.3.2. Okay, and it has been learned from, like, it has been 9 seconds since this particular router learned about that route, and the advertisement was received on SE2/0. Similarly, if you go on to the other router and check the same by saying do show IP route, you will also see a router. There you go. You have a route that has been installed with the help of RIP, routing information protocol there. Okay, and that particular route has been received via SE2 via 192.168.3.1. And now if I go back to the topology and if I try to send traffic from here to here, okay, the PC doesn't have any ports functional. I'm gonna go and configure the IP addresses on these devices. DHCP, and it's working. And then DHCP, and it's working fine. There you go. And then if I try to send traffic now, first packets probably would be failed because of ARP resolution, yeah. And then second successful. You see that? Then I can send traffic. First failed, second successful. There you go. And then I can send traffic over here and every communication will be successful there. Make sense? So this is how routing information protocol actually works there. I hope you understand that. Yeah. So go ahead, try this small configuration. The only command that we have used is uh, just a minute. The only command that we have used is network, uh, or when you go into router rip, yeah, router rip version 2, 192.168.1.0 and 192.168.3.0. Rest, you are familiar with the remaining configuration. So go ahead, try this particular lab up and see if it works for you. Okay, I'll give you around 10 to 15 minutes for that. And let me know when you're done. And then we'll move on with the next information that you need to be aware about RIP. Okay, thank you. Okay, as most of you are done, I believe, configuring the lab, we will move on and understand how exactly the RIP works there. Correct? Any questions from your side? Rizwan, you're saying hi there. Do you have any question? Yeah, am I audible to you? Okay, so I believe we can move on to the next thing that we had to discuss. Let me share my screen with you all then. Here. Right, I hope you can see my screen now. Perfect. So, as you can see, this is basically the topology that we have, which means if I specify how we are working over here, then you can get a view of it in a way that you have your directly connected network as 1.0 and 3.0, which are known to this particular router. And then you can also get to know that 2.0 and 3.0 are known to this router, which means the router actually, or both the routers actually have a common network, which is 192.168.3.0. You get that? Now, when I say the characteristics of packet tracer, which so we will discuss some of the characteristics as it's an open standard protocol. Then the second characteristics that we actually discuss is classful nature, correct, which means it can advertise the routes that are not classful, that are not of classful network. And then the third characteristics is updates are sent on 224.0.0.9. You get that? So when I showed you that the static route, or that whatever you have over here, whenever, not the static route but the route that is learned by the router, keeps getting updated every 30 seconds. Okay, which means that it uses periodic updates. RIP, routing information protocol, uses periodic update for 30 seconds. Every 30 seconds, your router is going to send an advertisement on on a destination address called 224.0.0.9. It is not going to send a unicast message to R2. It is going to send a multicast message, and that particular multicast message will target to the other host as well. Which means that if you have different host, if you have like connected with R3 as well and then connected with R4 as well, so this R2, R3 and R4, all these routers needs to receive the routing update from R1. So that's why R1 is not going to send individual packet to this router, then to this router, and then to this router. It is not going to work like that. The router or the RIP will just initiate a single message onto this destination, which is 224.0.0.9. And any router who has a routing information protocol configured on it is going to receive that particular routing update every 30 seconds. And by the way, this is one of the biggest drawback as well of routing information protocol, that it sends periodic updates every 30 seconds, and that's why it consumes unnecessary bandwidth. Okay, it consumes very unnecessary bandwidth there that it should not consume, because even if there is no updates or even if there is no changes inside your network, your routing information protocol is going to exchange the I would say route every 30 seconds, no matter what no matter how or what the network has been performing to. You understand that what I'm saying? So that's one of the characteristics there. Then, if we talk about the fourth characteristic, you can see that it uses metric as hop count. Now, understand this term very well. Can you tell me that if I look into my R1, or if I look into my router 1, then my router 1 actually has two different routes advertised. Okay, on router 1 we have advertised 1.0, and on router 1 we have advertised 3.0. So when R1 is initiating a routing update on 224.0.0.9, how many routes is R1 advertising? What do you say? Can I say R1 is advertising? Yeah, exactly. R1 is advertising two routes. But if I go into one of the router that is connected in my RIP, or if I go into R2, how many routes do you see over there? If I go over here and if I show you enable and conf t and show IP route, oh sorry, do show IP route. How many routes do you see? There is just one route that has been learned. I'm talking about this route. This is a route that has been learned by RIP, right? But our R1 advertised two route, which was 1.0 and 3.0. Why don't you see 3.0 as a RIP route? You of course have a route that says 192.168.3.0, but that particular route is not there as a routing information protocol route or as a RIP route. And why is that? Because it is connected directly. And what difference does that make? I mean, based on what terms the router actually identifies that it should not install the route that is learned by RIP into the routing table, and it should install the route that is directly connected to the router into the routing table. On what grounds does the router makes this particular choice? Exactly. So as RJ is saying in the chat that it is depending or it is making that particular choice with the help of the administrative distance or AD value that you have. Okay, because when we look at the topology, then you would basically see that the administrative distance or static route has an administrative distance of 1. Directly connected route has an administrative distance of 0, and a route that is learned by RIP has an administrative distance of 120. So when the R2 receives a route, one via static and the other one via RIP. However, the route is just like 3.0 and 3.0. Okay, even though after that the route, when I say static, I mean direct. Okay, directly connected network. So when I say that this particular router knows these route or knows this network with the help of directly connected network, then which has an AD of 0. So this particular lower value wins over the higher value of RIP. So whenever the R2 is receiving an update for 3.0, it checks the AD value of that and the router prefers the route that is directly connected. Okay, and it doesn't prefer the route that is not directly connected or that is connected, but the update about that is being given to it with the help of a routing update, and the AD of which is much higher than the route that is available there. That's why it's gonna make a choice of choosing the you can say directly connected route over the static route. Sounds good? That's one of the term over there. The second factor when choosing the best route to be installed into the routing table is the router is going to make that particular choice with the help of a metric value. And in RIP, the metric is basically used as hop count. Okay, so it uses hop count as its metric, which means if I have a parallel connection like this, I have an R1, I have an R2, I have an R3, and I have an R4. And I want to reach out to a network over here, 40.0.0.0/24 from here. So R1 will kind of decide that how many hops do I really need to cross in order to reach out to the destination network, which is 40.0.0.0. And in that scenario, the network is actually shown to you, or the network is actually visible with the help of checking that the R1 is actually reachable to R2, R3, and R4 by crossing like 3 hops. So it can reach out to 40.0.0.0 via R2, R3, and R4. So then the R1 will make an entry that 40.0.0.0 is known with the help of 120 AD and 3 hops away. You see that? And this particular information is called as metric. The value of that particular metric is called as hop count. And based on this hop count, since routing information protocol, or since every router that is using RIP makes its decision based on the distance that the network is situated at, it considers that particular value in order to calculate the best route possible. That's why it is called as distance vector protocol. It makes the decision based on the distance that the destination device is, or that the destination network is situated at. Do you understand what I'm trying to say? Yeah, perfect. And you can verify that particular thing into the routing table as well. That you will see this particular bracket value. I will show that to you as well. If you go over here, yeah, if you can check that R1 has learned this particular route, and this information specifies in the bracket that 120/1 is actually 1 over there is basically the metric of the destination device 2.0. Okay, that's how it decides that it is the best route possible. Yeah, it's 1 hop away. Okay, that's how it knows it. Then another important characteristics of RIP, which we need to discuss about, is if I talk about the fifth characteristics, then load balancing is supported, which means load balancing of 4 equal cost is supported. Your RIP, or your routing information protocol, supports load balancing of 4 equal cost. Now, what does this mean? Suppose you have an R1 router, and that R1 is connected to R2, R3, R4, and then R5. And this R2, R3, and R4 are connected to this R6 with just 1 hop away. But this R5 is connected to R6 by going through R7 like this. So can I say that R1 has a route, let's say that route is 60.0.0.0, okay? So R1 will make an entry of a route that is learned with the help of RIP, which is 60.0.0.0, and the AD will be 120, and the metric will be 2, it is 2 hops away, right? How many routes with the same details will R1 have? Can I say R1 can have 3 routes of such detail? Correct? And then, you don't get it? I am saying that you have an R1, right? And in that particular R1, you have R2, R3, and R4 connected over there. So, R2, R3, and R4 are giving, or they are advertising the information about R6's 60.0.0.0 to R1. and both of those, like all of those neighbors, which is R2, R3 and R4, they will actually have the information that 60.0.0.0 is connected to them, or they are giving the information about that particular route that they are connected via 2 hops away with R1, right? So R1 is going to add that particular route into the routing table. But the decision over here needs to be made that when I said that your load balancing of 4 equal cost can actually be made, it means that you have 3 paths that actually makes this particular network reached out. But this last route uses hop count of 3. That's why this is not same as the metric of the previous route that has been learned. Although all the routes are there and they all make you reach out to the destination network. But only the shortest distance route will be considered over there to be added into the routing table. And what is that route? The route that actually makes you reach out to R6. Okay, far like in a shortest with the shortest number of hops, which is R2, R3, and R4. So you have a tiebreaker, or you have 3 such networks that actually makes you reach out to the destination with the same number of hops needs to be crossed. But the last route needs to be like added into the routing table with the hop count of 3, not with the hop count of 2. That's why it doesn't become eligible. And only R2 and R3 and R4 will actually be able to install the route into the R1's routing table. Okay, because in that case they will do load balancing of 4 equal cost path. Okay, whenever you have multiple routes that actually has the metric value same for a same destination, then you call them as equal path cost, and then the traffic between equal path cost is shared. So you can have such four such equal cost routes installed into your routing table for one network. Do you understand what I'm trying to say? No, load balancing is not a tiebreaker. Load balancing is that one by one they will share all the packets. So your traffic will go with the first link as well, the second link as well, and the third link as well. Okay, but your traffic will not go via fourth link. No, the traffic will go with 120/2. Okay, why will it go via 120/3? It will not go via 120/3. Make sense? Perfect. So that's something that needs to be understood by you guys. Then after that, the next characteristics that we have, let me just get done with this particular thing. So the next characteristics is maximum hop that is allowed is 15. In routing information protocol, you cannot connect more than 16 routers together and send your traffic. You understand that? Which means if you have your R1 here, then you have your R2 here, then you have your R3, R4, like that, you can only have R15 in the serial connection. Okay, if you have your R16 and if you have your R17, then the network that will be advertised by R1 will not make it out to the 16 and 17 and any router after that. Your traffic can only go till the metric value that it reaches to 15. Do you understand that? That's why it has a characteristics that maximum hop that is allowed is 15 only. Okay, yeah. And as I've told you that they exchange the routing table every 30 seconds. So these are certain characteristics that RIP actually uses. I hope all of that characteristic is clear to you. No, Amar, you are not going to configure a network with the metric, right? With the hop counts. You basically receive advertisements there. And you receive advertisements with the metric value given inside of that advertisement. So if your router receives an advertisement that actually has metric 16, or that actually is coming from a router which is situated 16 hops away, then your router will not accept that particular traffic. Okay, it will drop that particular route, assuming that this particular route is not supported, and I cannot reach out to a router which, or I cannot send traffic to a router which is situated 16 hops away from me. So that particular route will not be installed into your routing table. Yep. These are certain characteristics of RIP and how it actually works. Yeah, let me clear the screen. And that was basically something that we had to discuss about RIP, you can say. Okay. Then there are certain things that we also need to discuss, which are RIP timers and all. But we will talk about those timers once we move on to the next protocol and all, and compare them with the pre-existing ones. Cool. The next protocol that we're gonna have is Eigrp. So we'll just take a short break of around 10 minutes and then we'll move on with the next one. Okay? All right, thank you. I'll see you in 10 minutes. Thank you. Hey there, I'm back, and welcome back to another session. Let's see. All right, as we discussed about how uh, our IP works, in comparison to that, we're going to see now how actually Eigrp works. So let me share my screen with you all again. Oh, it's already shared. Now we are okay. Just a minute. All right, there you go. I hope you can see my screen now. Is there any issue that we are facing? Mohammed is saying that web version 2, 1.0, 2.0 exit. Oh, Mohammed, you also need to advertise your routes onto the second router as well. Until unless you create your rep instance on the second router, it will not work. Do you hear me? So without that, it's not gonna work. Yeah. So when you will be done configuring routing information protocol on the other router, then it will start to work. Exactly. Now in this session, we're going to move ahead. So welcome back to another session of our CCNA training, and I am going to start with the session, or start this session with discussing Eigrp. Okay, as you can see that in the previous section we discussed about RIP and how RIP actually works. We're going to discuss some of the fundamentals of Eigrp, and then we'll move on and configure Eigrp for the same. So this was our topology that we actually used for routing information protocol, and we probably will be using the same topology here, but we'll just compare this particular topology with the other like with the contrast concepts that are available in Eigrp. But in order to be able to get to know about how Eigrp actually works, first let's get to know about the fundamentals that you have. So if we talk about Eigrp fundamentals, then Eigrp, as most of you might know, it stands for Enhanced Interior Gateway Routing Protocol. Correct? Enhanced Interior Gateway Routing Protocol. And it is called as Advanced Distance Vector Protocol. Okay, Advanced Distance Vector Protocol. So I'll talk about why this is called as Advanced Distance Vector Protocol, because we have seen how RIP actually works, and RIP has worked something which is called as Distance Vector Protocol. And why RIP is called as Distance Vector Protocol? Because it makes the forwarding decision based on how far the destination is situated, which means it takes the forwarding decision based on the number of hops that the destination network is away. If you have a scenario like you have R1, and then you have R2, and then you have R3, and then you also have a scenario where you are directly connected with R1 and R2, and then this R3 has a destination network of 30.0.0. Then even though that your R1 has a way to forward that traffic via this, or your network can actually forward the traffic via the other way as well. So based on that particular scenario, your router is going to, you can say, take some decision that how to forward that particular traffic there. Makes sense? And the decision is going to be made not based on how, like, what the link is connected, what it's connected with the link of, or how good that particular link is, but it is purely going to be based on something you can say. Just a minute. Why am I having this window here? Yeah. So if you have your R1 connected via two routes to R3, then it's gonna make this decision from either here, or it can forward the traffic from here as well. Okay. And as your router 1 will take the decision based on the number of hop away. So if it takes the first route, which is actually connected from R1 to R2 to R3, then it needs to cross two hops, right? But if it considers the second route, which directly connects R1 with R3, okay, then it just needs to cross one hop. And that's why this particular route becomes the winner. Okay, and then the R1 will basically forward the traffic based on this particular route over here. Do you understand what I'm trying to say? This is how distance vector protocol actually works. But over here, as I told you, even if the link that is being connected between R1 and R2 and R3 is, let's consider that the link is made up of 1 Gbps. This is a 1 GB link and this is a 1 GB link, and the other link is of 100 MB. So even though the number of hops for the second link, okay, it's just one hop that R1 needs to cross in order to reach out to the destination. But if we look at the other route, which is the first route, then the link is faster, even though it needs to cross two hops. So even though the bandwidth is faster and in real time, your traffic will actually reach out to R3 faster if you send it via R2. If you have configured routing information protocol, then your traffic will still go via R1 to R3, which means by taking the second out, because RIP works based on, not based on how fast the link is, but based on the information that how far the destination is. Okay, that's why the number of hops is an important criteria, or it's the only criteria that is considered while choosing out the best path in routing information protocol. Do you guys understand that? Let me check that. Perfect. So when I tell you about the same thing there, so yeah, when I'm actually talking about that EIGRP is an advanced distance vector routing protocol, what I mean that it doesn't only consider the fact that how far your destination is, but it also considers the other parameters of the network as well, be it bandwidth, be it load, be it something else, and it's gonna take the decisions based on that particular information. So that's one of the second criteria that EIGRP considers. The next factor that the EIGRP will consider over here is that if we talk about the next factor, then EIGRP, let me change the color of that. Yeah. So the third parameter over there is very common, that it's classless routing protocol. Okay, just like RIP. So it supports classless behavior of it now. Yeah, as I was telling you, that it supports the classless routing protocol, or it is classless behavior of it. Makes sense? And then after that, you can say, which means that you can send traffic, or you can advertise your network of /24, or be it /27, be it /28, or something else as well. Okay. Then if we talk about the next one, then you can say that it is an enhanced version of the predecessor. So you can say it includes all features of uh, IGRP. IGRP stands for Interior Gateway Routing Protocol, which was a previous version of EIGRP. And EIGRP is just like you have RIP version 1 and just like you have RIP version 2. Okay, there was, first of all, in comparison to RIP 1, you had IGRP, which is Interior Gateway Routing Protocol. And then you have EIGRP in comparison to RIP version 2, which is an upgraded version of IGRP. Okay, so this is how the transition actually worked. So EIGRP contains all the features of IGRP, and then it has some additional features of it as well. So you can say that it includes all the features of IGRP, and after that, there is no, you can say, caring that is done, because the maximum hop, or the max hop supported, or the max hop count in EIGRP is 255, which means you can have R1, you can have R2, you can have R3, and just like that, you can have 255 routers that can actually be serially connected, and your traffic will still reach out to the 255th router there. However, if you consider that the default value for the maximum hop is only set to 100, okay? So by default, your packet cannot or your traffic cannot go beyond 100 routers, but you can increase that particular value to 255. Make sense? So just like that, you don't need to actually worry about the number of hops that you have because you're not serially going to be connected with that many routers in the production environment. There can be scenarios of the very big environment there, but yeah, then there are other protocols that are also considered over there for creating the connectivity. Okay, this is one of the parameters that you have. Then after that, what you need to consider is the AD value of Eigrp is 90. Okay, so just like RIP has an AD value of 120, Eigrp actually has two values. Okay, you have 90 and you have 170. So this 90 is for internal networks and this 170 is for external networks. Okay, which means that basically whenever you exchange a route between one organization, you call those particular routes as internal routes. Okay, the subnet might be different, but if you want to, like you can say, import the routes of some other organization or some other, you can say, building inside your primary building or so, then those routes will be considered as external routes and Eigrp treats them differently. Eigrp has a different administrative distance value for them. Okay, but that's none of our concern as of now because we're still about to understand how Eigrp works in that concern. So you can just understand this particular thing, or you can just note this particular down, or note this thing down that Eigrp has two values, two AD values or administrative distance values. Okay, one is 90 and the other one is 170. And yeah, the Amar, yeah, as I told you that the RIP has an AD value of 120. Okay, RIP uses an AD value of 120 there. Then after that, you can say Eigrp is considered as 100% loop-free protocol. This is just one of the characteristics that for now you can just write it down that it's 100% loop-free protocol and it doesn't create any loops. Okay, because of the behavior of how it actually behaves. Then if I talk about the next parameter, then you can say that the updates, routing updates are sent on 224.0.0.10. Okay, so routing updates are sent on 224.0.0.10. RIP used to send the routing updates on 224.0.0.9, but over here there is one such a big difference between RIP and the Eigrp over here that if you consider RIP uses something called periodic updates. Make sense? And Eigrp uses something called triggered updates. What does this mean? So, for example, if you have a network like this, and then there are multiple networks. This is one switch, this is another switch. You have PCs communicated over here or connected over here. This is 1.0, 2.0. And then you have another network over here, which is 3.0 and it is connected with 4.0. Do you understand this topology? So for now, you can consider this in a way that let's say there is communication that is happening from here to here, from here to here. You get that? So your Eigrp or your RIP, your routing information protocol, is going to exchange traffic between R1 and R2, which will be called as routing updates every 30 seconds. You understand that? Now let's assume that there is this new network that actually got attached with R2. Okay, and this particular network is called as 5.0. So RIP instantly will kind of advertise that particular new route, and it will create instantly a new route, like routing update. And then again, it will carry further that particular advertisement every 30 seconds. So this type of scenario, we understand it with something called periodic updates. But this is not how EIGRP actually works. Okay, EIGRP works on triggered updates, which means if you already have your network converged, which means this is your network. And at the beginning of when this network was actually being built, for the first time, the routers will exchange the routing updates by creating something called neighborship, EIGRP neighborship. Okay, and once the entire routing table is exchanged, or once the routes that are advertised are exchanged between the neighbors, then there won't be any update that will be sent. Okay, and if there is any new network that comes up that we had, like let's say 5.0, then and then only R2 will initiate a new, you can say, packet that says, hey there R1, I have an update for you. There has recently been a new network that has been added into my topology, and here's the detail of that particular network. So then R2 will give the details of 5.0 to R1. Do you understand that? Even you need to understand over here that R2 is only giving the change, not the entire update again and again, like what RIP does. If this particular change would have been made into RIP topology or routing information protocol topology, then the RIP router would have been given the entire routing table again to the R1, that hey there, this is my entire you can say routing table again, and make changes into your routing table accordingly, because there is some change in my network as well. But EIGRP doesn't exchange any routing update until unless there is any change in the network. And whenever there is any change in the network, the router is only going to advertise that specific change and not the entire routing table. Do you understand the scenario? Yeah. So that is what the behavior of EIGRP is. It means that routing updates are sent on 224.0.0.10. Okay, again, I'm telling you that the update that R2 will give, which is going to be a triggered update upon a change in the topology, will again not be any unicast message. It will be a multicast message that will be sent on 224.0.0.10. Okay, and you can check the current routing table manually over there to see if there is any change in the network. Okay, you can do, yeah, all those modifications can actually be done. Yeah. And yeah, that's exactly what triggered update means. Okay, and EIGRP works according to the triggered updates and not the periodic updates every 30 seconds like that. And this kind of behavior of EIGRP saves a lot of unnecessary bandwidth utilization that gets done by RIP if you have RIP in your topology. Makes sense? So yeah, that's one of the attributes there. Let me clear this window here. Then the next characteristic of EIGRP that you can see over here is hello packets are sent every 5 seconds. You see that? Hello packets are sent every 5 seconds. Now, what does this particular thing mean? Now, if you consider a topology that you have in RIP, I'm going to again create the same topology that you have R1 here and that you have R2 here. And then in R1, you have a network like this, and then you have R2 and you have a network like this. You have 1.0, 2.0, and 3.0. So in such scenario, how are you going to keep your network updated? Let's assume that the network that you're talking about is no longer available, which means there is any layer 1 or layer 2 or layer 3 issue, and due to that 1.0 network is no longer available. So how would the other router in RIP will get to know about that? So that's why in RIP there is something called RIP timers. Okay, and when you talk about these RIP timers, then you will actually get to know that the first type of timer that you have is update timer. Update timer, which is of 30 seconds for the periodic updates, right? So whenever you like your router will send you a routing update every 30 seconds, irrespective of whether there is any change or not in the network. We already have discussed about this. The second type of timer that you have here is called as invalid timer. Okay, and this invalid timer by default is set to something called 180 seconds, 6 times of update timer, which means if this network goes down, then until unless 180 seconds, R2 will keep on waiting for that particular update, which means before R2 removing that particular route from its routing table, it will wait for 180 seconds for that route to come back again. Okay, because as soon as the route goes down, then R1 will stop advertising that particular route from the next update. Do you understand that? From next update, R1 will not advertise that route because R1 will get to know that, hey there, my 1.0 network is down. I cannot advertise that particular route anymore. But still, R2 will maintain the previous information about 1.0 till 180 seconds. Makes sense? In a hope that in like within 180 seconds, the network admin will try to fix something and the network will come back up again. So in order to save the extra processing, R2 kind of maintains that particular route into the routing table until unless invalid timer crosses. Then there is a third timer called flush timer. And this flush timer is set till 240 seconds. Which means that after 240 seconds, the router removes that particular route from the routing table. Make sense? This is exactly how the communication actually works. And in CCNP, you will learn about all the disadvantages of this behavior of RIP. Okay, because due to such behavior that it maintains the route for certain amount of time, even after the route is no longer available. Okay, due to such behavior, there can be loops created and there can be some other scenarios that can actually harm the network. And yeah, these timers are not editable. These are the fixed timers that you have. Okay. So far we are like concerned about RIP. RIP's timers cannot be modified over here. Make sense? So update timer basically is the time between the consecutive updates that R1 actually sends. Then invalid timer that we discussed is basically a time a router waits to hear an update from the router or from the other router that the route was actually learned from. And you can say the route is marked unreachable if there is no update during this time interval. And the third timer, as I told you, is a flush timer, which actually you can say is a time before the invalid route is removed from the routing table. And then there is a fourth route as well, which is called as a hold down timer, which is again called as 180 seconds. Okay, so this invalid time and hold time is actually same, and you can say that This particular timer stabilizes the routing information and it helps to prevent the routing loops during the periods when the topology is actually changing to the new route or so. Okay, so the invalid time and hold time are kind of same, you can consider that. But yeah, these timers are basically there to help stabilize the network when the router or when the topology is actually struggling for fetching out the new way that it can reach out to the destination network also, if some route goes down also. It is also possible that this route is not available and then the R2 is actually connected with some other route with R1, right? So there can be multiple scenarios that can be created in order to understand how each of these terms can be created, but you will learn about that in CCNP. For now, you can just consider that these are the timers of RIP. Now, EIGRP doesn't work with such timers here. Okay, you have multiple of these timers, but if we talk about EIGRP, as I was telling you, over here that yeah, flush timer. Yeah, flush timer means that the network will be removed from the routing table, correct? It's about flushing the route from the network, not about flushing the entire network. It's possible that your router is exchanging multiple routes and one of that route is no longer available. So it will remove that particular route, that specific route. Not all the routes, but the specific route which is not being sent by the router anymore in the routing update. And it will remove that after the flush, like during the flush timer. Okay. So as I was telling you that EIGRP exchanges hello packets. It's flushing is basically flushing the specific route, not the entire route. Yeah. So EIGRP uses hello packets in order to exchange traffic every 5 seconds. It doesn't send the routing update every 5 seconds. It sends hello packets every 5 seconds. Make sense? We'll talk about that in a bit, that how this hello packets and all works over here. But for now, you can just have an understanding that EIGRP uses hello packets in order to stay connected with the neighbors that it has or with the routers that it's exchanging the routing table or so. Make sense? So, and then the last characteristic that you need to be aware about is it uses a protocol called dual. Dual stands for diffusing update algorithm. Okay, EIGRP uses dual algorithm or diffusing update algorithm in order to calculate the best route that is there. Sounds good. And we'll talk about how this diffusing update algorithm works. And the last characteristic that you have is it supports both equal and unequal cost load balancing. Unequal cost load balancing. So it supports both equal and unequal cost load balancing. That's exactly how it actually works. Sounds good. So these are certain characteristics that you have about EIGRP that you actually need to understand. Okay, and I hope that makes sense to you. Okay, however, some of them like how dual works and how equal cost and unequal cost load balancing works, we're going to talk about that in just like now 2 to 3 minutes that we're going to talk. But let me know if you understand all of these characteristics like as part of the basic thing. Are we good here? Perfect. Just give me a minute and then we'll go ahead with the next one. Just a minute, guys. I'll refill my water bottle and we'll be back in a minute. Yeah, hey there. I am back. So, as we discussed about the fundamentals of Eigrp, it's actually time to discuss how the thing works here. So, the process can be identified with something called Eigrp, neighborship. Okay, and you can consider it as Eigrp, or you can consider Eigrp neighborship in a way that it's a two-step, or you can say multiple-step process in order to create Eigrp adjacency. So you can have your R1 there, and then you can have your R2 here. And let's say both of these routers are actually initiating to create Eigrp neighborship between them. And you can understand it in a way that the R1 and R2 are actually having a network called 12.0.0.24. Dot 1 is here and dot 2 is here. Okay, so whenever this R1 and R2 will actually try or configure the EIGRP and advertise the network, then it's not like that instantly they will exchange the routing information. It doesn't work like that. Okay, whenever you have two routers that are creating an EIGRP neighborship, then they actually go through a series of process in order to become EIGRP neighbors. Make sense? So when we talk about it, it actually starts after configuring EIGRP onto the router. The very first procedure that both the routers will start sending hello messages on 224.0.0.10. They will send multicast hello messages on this particular address, and any router that actually has configured EIGRP will receive that particular hello message. So R1 will also send that, and R2 will also send the hello message on the same address to 24.0.0.10. You get that? Then they actually need to become neighbors, because inside of this hello message, yeah, what's gonna happen over here? That let's assume that I go into R1 and then I configure my EIGRP into R1 and advertise my network. Then I go into R2 and I also start configuring EIGRP, and then my EIGRP is configured on. As soon as I configure EIGRP on my router will start sending hello messages on a multicast address that, hey there, is there anyone who has configured EIGRP? I would like to become neighbor with you. Hey there, is there anyone who would like to exchange routing or routing information with me? I'm running EIGRP, like that. It will contain some of the other information, and the hello message will be dispersed onto this destination address called 224.0.0.10. And the hello message contains three neighborship parameters. So you can consider that there are neighborship parameters. The first neighborship parameter is that both the routers who are actually exchanging the hello messages or receiving the hello messages, or who are looking forward to become neighbor, needs to be in same subnet. Okay, they need to be in same subnet. Like you have 12.0.0.0 configured, right? So R1 and R2 are into same subnet via that particular link. You get that? Then the next parameter there is they needs to be into same autonomous system number, same ASN value. So how it works in RIP, if you have R1 and then if you have R2, then you simply go on R1 and you say router RIP version 2 and then network this, network that. Correct? But in EIGRP, it doesn't work like that. In EIGRP, whenever you have multiple routers, then those routers will only be able to exchange routes if they are into the same autonomous system number. Which means if I go on R1 and I say router EIGRP 10, okay, then this 10 is called as AS number, autonomous system number. And if I go on R2 and say router EIGRP 20, then I'm configuring a different AS number on R2, and these routers will not be able to exchange the routes. Do you understand what I'm trying to say here? Which means that for you to be able to exchange the route, your both the routers actually needs to, you can say, exchange the route, or both the routers actually needs to exchange the route with having same autonomous system numbers configured on them. You understand that? So your routers are only going to become EIGRP neighbors if both of them are having same autonomous system number configured there. Okay, that's one of the condition there. And then after that, when you have this particular scenario there, the third parameter that is available there is, just a minute. Yeah, screen is just being delayed, just a minute. One minute, guys. Yeah, I just stopped and shared my screen again. And yeah, as we were discussing about EIGRP neighbors, right? Or EIGRP neighborship. And I was telling you that when you have your R1 and then you have your R2 configured there, and both of them are in a same subnet. Okay, you can have .1 configured here, .2 configured over here. And I was telling you that your R1 will send the hello message on 224.0.0.10, and you will get a hello message from the reply as well as 224.0.0.10 as well. Correct? But in order to become neighbors, there are some neighborship parameters. And the first neighborship parameter is that they should be in same subnet. The second parameter, as I told you, that they should be in same autonomous system number. And the third parameter is they should have same K values. Okay, now K values is something that we are going to discuss about later. But by default, EIGRP has multiple K values configured here. Okay, your EIGRP has almost 5K values that actually helps the router in deciding what is the best route. It is part of the diffusing update algorithm that it uses in order to calculate the best route. But yeah, you can consider it like that, that EIGRP uses all these three parameters in order to decide whether it can establish EIGRP neighborship with the router or not. And once all of these routers or all of the neighborship parameters are matched, then and then only they both the routers will actually become neighbors. Okay, and then EIGRP also maintains something called EIGRP tables, and inside of that the first table is called as neighbor table, and the information about your neighbor will be stored inside the neighbor table. upon exchanging the information with the help of hello packets. Do you understand this? Perfect. Then after exchanging the Eigrp information here, what's going to happen is your router then will process in exchanging the routing table. After becoming neighbors, then your R1 will say that here is my routing table. Do you understand that? And then R2 will acknowledge to that particular exchange that, hey there, I have received your routing table. And then after that, it will say, here is my routing table. Makes sense? And then R1 will acknowledge to that particular exchange that I have received your routing table as well. And then there is a second table into Eigrp table, which is called as topology table. And the information about this routing table, or all the routes that will be received, will from the neighbor will be stored over here into the topology table. Makes sense? And then the best route will be installed into the routing table, which is the third table. And once the best route is installed from the available routes into the routing table, then the network will become on a stage called converged. You understand that? So this is actually how it works. Now, here's something that you need to understand, that what is this transition between topology table and routing table? So, for example, let's consider a scenario over here. I'll give you that scenario, that you have something, you can say R1. And with this R1, there are multiple routers that this Eigrp is neighbor with. So you have this R2, you have this R3, and you have this R4. And this R2, R3, and R4 is also connected to another router called R5. Do you understand that? Now R1 has a loopback address called 10.0.0.0, and R5 has another loopback address called 50.0.0.0. And this is the source, and that's the destination of how your traffic needs to actually communicate. Now, can you believe, or can you, when I say that R1 is actually neighbor with R2, with R3, and with R4. And in order to get to know that how to reach out to this destination network of 50, R1 is going to inquire to R2 and R3 and R4. Do you trust that information? That R1 is going to ask to its Eigrp neighbor that, hey there neighbors, do you know any information about how to reach out to 50.0.0.0? And it is possible that R2 has multiple routes that how it can reach out to 50.0. For example, R2 knows about around 3 routes that how to reach out to 50. R3 knows about around 2 routes that how to reach out to 50. And R4 knows about around 5 routes that how to reach out to 50.0.0.0. And all this information, which means that combining all together, the neighbors knows somewhat around 10 routes that how to reach out to the network. Now what's going to happen here, that the R2 will give only the best route out of the available 3 routes to R1. Then R3 will also give its best route to R1, and R4 will also give the best route available to it in order to reach out to 50.0.0.0 to R1, which means R1 is going to receive 3 of the best routes that its neighbor knows about for reaching out to the 50.0.0.0. And all these 3 routes that it will receive from the Eigrp neighbors will be stored into something called topology table. Do you understand this? And as I told you that your topology table is going to have almost 3 routes now. And the best route amongst these 3 routes, only one best route is going to be inserted into the third table called routing table, which means that your topology table can have multiple routes, but only the best route will be inserted into the routing table. And selecting this best route is basically the process of diffusing update algorithm. Okay, dual algorithm does the task of this. Again, we are going to talk about what this dual actually does. But yeah, this is how actually EIGRP does the process of bringing the network up. Okay, and this is how EIGRP neighborship is built up. Make sense? Perfect. Now we're going to see in a topological manner that how you can actually create EIGRP neighborship between the router. Okay, so I'm going to create a simple topology and I'll show you how you can create EIGRP topology by configuring the network with the necessary configuration there. Okay, so I'm gonna erase the stuff up from my script, from my screen. There you go. And then I am going to have a couple of routers here, or let's say we're going to have around 3 routers. And I'll also place 1, 2, and 3 there. And I will place a couple of PCs along with that. And then I'm going to connect all of these together by connecting it to R1, connecting it to R2, and connecting it to R3. Okay, we probably need another device there. So yeah. And then we are going to connect these together as well. Okay, that's how we have the thing here. We have 1.0. Oops. Okay, my note is not working, so coordinate with that. So we have 192.168.1.0. We have 192.168.2.0. We have 192.168.3.0. Then we have 192.168.4.0 and 5.0. It's better that I note it down there. But like that, I will just note it down as 192.168.1.0/24, 192.168.2.0/24, and then I have 192.168.3.0/24 and 192.168.4.0/24 and 192.168.5.0/24 as well. You get that? Just like that. So what we are going to do now, we will basically configure this entire network by configuring the IP parameters first and then by configuring the EIGRP. So I'm just going to go on each and every router there. Yeah, I'm just going to go on each and every router there and configure it. I'm going to go on to the first router. I'm going to say no, enable conf hostname R1. Oops, hostname R1. Yeah, and then I'm going to say interface FA0/0, no shutdown. IP address 192.168.1.1 along with the subnet mask, and then IP DHCP pool A network 192.168.1.0 along with the subnet mask and default of 192.168.1.1. Then I'm going to take an exit there and I'm going to say interface SE2/0, no shutdown, IP address 192.168. What's the IP that we're going to configure there? Yeah, 4.0 network, so I'm going to configure 4.1 over here. So I say 192.168.4.1 along with the subnet mask there. And that's all. So we're good with the configuration of R1, and I'm going to go onto the PC of R1 and configure IP address for the host that we have. There you go, DHCP. Then I'll close this router and go back to the second PC, desktop, IP config and DHCP. And there you go, it's working fine. Then I'm going to go on to the R2 and configure three of these networks, 2.0, 4.0 and 5.0. So I click on this, go to CLI and say no, enable configure terminal, interface FA0/0, no shutdown, IP address 192.168.4.1, sorry, 2.1 along with the subnet mask, and IP DHCP pool B, network 192.168.2.0, 255.255.255.0, and default of 192.168.2.1, right? Then I'm going to take an exit, say interface SE2/0, no shutdown, IP address 192.168.4.2 along with the subnet mask, and then interface SE3/0, and I'm going to configure that with IP address 192.168.5.1 along with the subnet mask. Makes sense? That's how the configuration actually will be done. And then after that, I am going to the PCs and configure the DHCP addresses there. There you go, it's done. And then after that, if I go here and desktop, IP configuration, DHCP, and there you go, 2.3 has been configured here. Then the configuration will be done for the last router there. I'll close down the PCs here and go back onto the third router. Enable config T, hostname R3, interface FA0/0, no shutdown, IP address 192.168.3.1, 255.255.255.0, IP DHCP pool C, network 192.168.3.0 along with the subnet mask, and default -router 192.168.3.1 along with no subnet mask needed there. Then going into interface SE2/0, no shutdown, and IP address 192.168.3. Sorry, not 3.1. It's gonna be 5.2. And there you go. The configuration is done. Then we will go onto the PCs of the R3 and configure the IP addresses there. There you go, IP done. Then I'm gonna go on to the last desktop, IP config and DHCP. And there you go. Then I'm gonna close this down, go back to this, and yeah. So right now, if I check the routing tables of our R1, there will only be directly connected networks, right? So if I say do show IP route, we just have 1.0 and 4.0. On R2, yeah, then on R2, if I go and say do show IP route 2, 4, and 5. Then after that, if I say do show IP route 3 and 5, 3.0 and 5.0, right? So we just have the directly connected networks over here. So when I do configure this particular network here, then we are going to have the same autonomous system number for 3 of these routers. Okay, the Eigrp autonomous system number that we're gonna have is just 10. So I'll kind of create a design over here by filling up a color, let's say a green color, say okay. And that's how the scenario will be. Yeah. You get that? So that's our EIGRP domain there. 192.168.1.0, 4.0, 2, 3, and 5. All of these networks are going to be part of our EIGRP autonomous system number 10. And how do you do that? It's pretty similar to RIP that we have did, but the only change over here is going to be router EIGRP 10. So we're going to go into EIGRP 10 there. Just a minute. Okay. Yeah, there you go. I hope my screen is back. So this is the topology that we have, right? R1, R2, and R3. And we are going to create an EIGRP domain here on R1, R2, and R3, which is going to be EIGRP number 10. That's going to be the autonomous system number that we have. So what we're going to do here, we're going to say router EIGRP 10, and then we would say network space 192.168.1.0, and then we're going to say 4.0. So just create EIGRP process and advertise both of your networks. That's how easy it is. Okay, then go on to the next router, which is our R2, and then check your routing table, do show IP route, and then I would say router EIGRP 10, network 192.168.2.0, 4, oh sorry, no, that's a false route that I have advertised. So I'll remove that route by saying no network. And then I will advertise the correct route, which is 192.168.4.0 and 5.0. There you go. You see, instantly there is an update that says new neighbor adjacency is up. And then I will advertise my next network, which is 192.168.5.0. See that? And then we will go on to the next router and advertise these. So I'll say router EIGRP 10 and network 192.168.5.0. There you go. New neighbor adjacency done. And 3.0. You understand that? So as of now, our entire network is converged. And if I try to send traffic from here to here, the first packet is going to be failed. And there you go, successful. And then from here to here, first fail, successful. So the communication is working all good from here to here, successful. Make sense? So you can see as soon as we advertised our network, it built up an EIGRP neighborship, and it is done so fast. Yeah, it is correct. Now, as I told you, there are 3 tables, right? You can check your neighbor information by running do show IP EIGRP neighbor. Okay, when you run this command, you will get to know about the EIGRP neighbor that you have. Just a minute. Yeah. So when you run this particular command that says do show IP EIGRP neighbor, you'll get to know about the neighbor that you have, which is just one neighbor, which means that if you look at the perspective of R1, R1 is not directly communicating with R3. R1 is only communicating with R2 for now. And if you go on R2, which is this router, and if I say do show IP EIGRP neighbor, you see, R2 has 2 different neighbors. It has 4.1 as well, and it has 5.2 as well, which means R2 is neighbor with this segment as well, and R2 is neighbor with this segment as well. I will delete this part here. So that's how actually it works here. Okay, and the EIGRP number 10 over here represents our autonomous system number. So this EIGRP 10 or 10 can be anything. When I say router EIGRP, and if I give a question mark, you can see that it is autonomous system number and it can be anything between 1 to 65,535. I have randomly taken 10 there, but you can take 20, 30, 40, whatever you want. Okay, and you can build multiple EIGRP processes with the help of that. So when you have this autonomous system number common between the routers that you want to actually exchange the routing traffic, then and then only it will work. Otherwise, you won't be able to create neighborship between the routers that are having different autonomous system numbers. And then if I go on to the third router and do check by performing a command to show IP EIGRP neighbor, then there you go. You just have one neighbor, which is R2 5.1. And then after that, you can also check the routing table by saying do show IP route, and you will see that there are these EIGRP routes that are advertised or that have been received on this particular router, which are 2.0, 3.0, and 5.0. Make sense? So 90 is the AD value, and this, whatever this number is, this is basically the metric that it calculates the number according to. Okay, for the best path selection. It's a big number, but we're going to talk about how EIGRP actually calculates the metric. So don't worry about that. Okay, we're going to talk about how this number is coming up. But you can, for now, you can consider that this is combination of bandwidth and delay. Okay, for reaching out to the destination. And then you can also check the topology table by saying do show IP EIGRP topology. And this is the topology table that you have. Okay, and inside the topology table, you have all the routes that are exchanged 1.0, 2.0, and passive means the routes are placed into the routing table. Active means dual is actually calculating something. Okay, or the best route is being calculated, but the process is done so fast, it's very rare that you will ever see active or any other state over there. You will always see passive and passive and passive. Okay, and you learn about every characteristics that you have here inside the EIGRP in CCNP studies. Okay, so this is how you actually get to know about the all the three routes or all three tables that EIGRP maintains, and then how you can actually make the communication possible by using EIGRP. Sounds good to you? Perfect. So go ahead, try this particular topology configuration and see if it works for you. The commands were pretty simple. I'll show those commands to you. There you go. 1.0, 2.0, 3.0, and I actually configured it by just saying these were the commands that I used for the directly connected network of mine. This is my routing table, and that's the command that I used. So go ahead, try this particular thing and see if it works for you. I'll see you guys in around. Yeah, you can check router 2. This is router 2. Yeah, go ahead, check this particular configuration. See, and I'll see you guys in around 10 minutes when you're done with the config. Thank you. All right, guys, I hope you are done with the lab. And then there are just certain things that I want you to know about it, or to know about the EIGRP. So here's the thing. We are going to talk about how EIGRP calculates the best route. So let me just share my screen with you, the other screen with you. And there. Yeah, I hope you can see my other screen now. And we are going to discuss something about EIGRP metric. So in EIGRP has five different values which are addressed as K1, K2, K3, K4, and K5. Okay. K1 stands for bandwidth, K2 stands for load, K3 stands for delay, K4 stands for MTU, and K5 stands for reliability. So by default, only K1 and K3 is working, which means bandwidth is set to 1 and delay is set to 1. Rest of the values are set to 0. And if you look at the formula that EIGRP uses in order to calculate the metric or the best route, is it's quite complicated, but yeah, metric in EIGRP is, I'll give you a simple formula that it uses bandwidth plus delay multiplied by 256. Okay, which means that if you have a route like this, R1 to R2 to R3, okay, and to R4, let's say, then from R1 to R2, if the link is of 100 Mbps, and this is also of 100 MB, and this is also of 100 MB, then in that case, the bandwidth is the least bandwidth from source to destination, which means if one of the link, or if let's say this particular link is of 10 mbps, and then this is your source and that's your destination, then the bandwidth that will be considered is going to be 10 MB and not 100 MB. Do you understand that? So it will be the least bandwidth or the minimum bandwidth from source to destination. Okay, but if you have a common bandwidth, which is like let's say combining all together, if you have 100 MB, then it will be considered 100 MB itself. And then the second formula or the second value that will be considered over there is going to be delay. And delay is the combination of delay from source to destination, from S to D, which means, for example, I would say the delay into the, for a fast Ethernet link, is for a 100 MB link is, let's say, around 100 milliseconds. There's going to be 100 milliseconds over here, 100 milliseconds over here, and 100 milliseconds over here. So totally it's going to be 300 milliseconds. So this particular thing will be the combination of delay from source to destination, like a time taken from for a packet to travel from one router to other router, and then it will be just a single 100 or 100 mbps is going to be the bandwidth. So For calculating that, it will be something like 100 plus 300 multiplied by 256, and the output of that will be the metric that you will actually see when you perform a do show IP route. Then you see in a route that you will find 90 as the AD and some value. That particular value is actually the output of this. Do you understand that? However, figuring that out is none of our concern as of now. But yeah, this is how actually Eigrp calculates the metric. Then it is not the only thing that Eigrp needs to deal with, because Eigrp also works in a way in order to figure out what is the best route. For example, if I say dual over here, diffusing update algorithm. So when we try to figure out how dual actually works or diffusing update algorithm works, then there are certain conditions. Let's say you have a scenario like this. You have R1, you have R2, you have R3. I'll draw the same topology, and you have R4. And then you have a destination, which is R5. So over here, consider that the metric from R1 to R2 is 10. From R2 to R5 is again, you can say 10. Then from R1 to R2 it's 15 and 15. And from R2 to R3 is 30 and 50. You understand that? So over here you need to calculate different values, or Eigrp calculates different values here. First of all, you figure out what are the candidates or candidate routes, because if you consider our scenario, then we have three routes, right? The first route is from R1 to R2 to R5. The second route is from R1 to R3 to R5. And the third route is from R1 to R4 to R5. Okay, these are the three routes that you have. And based on that particular route, you need to calculate two values. You need to calculate something called FD, and you need to calculate something called RD. Now, what is this FD and RD? FD stands for feasible distance, which means combination of total or combination of metric from source to destination. And RD is stands for reported distance, which is the metric from next hop to the destination. For example, if you have R1 to R2 to R3 to R4, and then you have 10, 10, 10. These are the metric. What will be the FD in that case? Can I say 30? Because from source to destination, this will be your FD. And what will be the RD? RD will be from next hop to the destination, which is going to be 20. Do you understand what I'm trying to say here? The difference between FD and RD? Yeah. So you can consider that the FD is going to be the feasible distance. I'll repeat the same thing. As I told you, that there are two terms every route is addressed with. Okay. You have feasible distance and you have reported distance. When I calculate the bandwidth, or when I calculate metric between two routes, let's say R1 and R2, this particular metric will be calculated with the help of bandwidth plus delay. Okay, and then it will be calculated in a way that the best route is possible. So it's possible that R1 to R2, and then to R3, and then to R4, you have these four routes connected serially, and every route, according to the bandwidth calculation, has a metric of 10, 20, and 30, let's say. Okay, this is the scenario. So what will be the FD, the feasible distance from source to destination is going to be the combination of all the metric throughout, which means 10 plus 20 plus 30. It's going to be 60. Do you understand that? And then RD is going to be the value from next hop to the destination, which is 20 plus 30, that will be 50. Make sense? Yes. So this is how these are the two values that Eigrp calculates in order to figure out the best route. Now, based on our example that we have, the FD for the first route from R1 to R2 to R3, what will be the FD there? Can I say the FD will be 30? Sorry, the FD will be 20, right? 10 plus 10. And the RD will just be 10 there, the next hop route. Then for second router or the second route, the FD will be 15 plus 50, 15, which is going to be 30. Okay. And the RD is going to be 15 itself. And then for the third route, it's going to be 30 plus 50, which is 80. And then the RD is going to be 50 itself. Make sense? This is how FD and RD can be figured out. Now, here's the thing. Based on these values, the router needs to figure out two values. One, it figures out successor, and it figures out another thing which is called feasible successor. Okay, it calculates successor and it calculates feasible successor. What is successor? Successor is basically best route, and feasible successor is next best route. Do you understand that? Successor is the current best route from the topology table, because as I have told you, topology table can maintain multiple routes over there. So when I consider this, it means that successor will become the route which with the lowest FD. The route which has lowest FD becomes successor. In our case, who will become successor? First route, right? So this particular route becomes successor. And this route will then be installed into the routing table. Do you understand that? Okay. The route which has lowest FD will become successor, and that particular route will be installed into the routing table. And then what about the other routes? So in order to other route actually intend to become feasible successor, which means if the first route goes down due to any L2 issue, layer 3 issue, or any link failure or so, when that particular route goes down, EIGRP should know the next best route that needs to be placed into the routing table. Okay, so it doesn't wait for the recalculation. It already knows about the next route who is going to be installed into the routing table. Okay, so for that, it actually needs to know about who is going to be the next best route, and that it addresses it as the feasible successor. Now there is something called a feasibility condition, and feasibility condition means in order to become feasible successor, the RD of candidate, just a minute, the RD of candidate must be lower than the FD of current successor. Understand this very well. Okay, in order for a route to become a feasible successor, the RD
or the reported distance of the candidate route must be less than the FD of the current successor. In our case, who is the current successor? This route, right? And who are willing to become feasible successor? Both of these routes. So for the second route to become feasible successor, the RD of that route must be less than the FD of the current successor. And does it satisfy the condition? Is 15 less than 20? Yes, right? So that's why this particular route will become the feasible successor. It's quite complex, but yeah, if you understand it clean and neat, then you will make more sense of it. And what about the third route? Does third route satisfy the condition to check whether the RD is less than the FD of the current successor? If you consider the value is 50 less than 15. No, right? So that's why that's why what's going to happen? Then the router will drop this particular route and it will not accept that particular route, or it will not insert that route into the topology table for now. And that route will not become anything. And the route, which is this one, the first route will go into the routing table, the second route will stay into topology table. If the first route goes off, if anything happens to that, then the second route, which is the feasible successor, will become the successor then, and it will be placed into the routing table. Do you understand how this works? Perfect. So that is exactly how it actually works. Okay, and I hope you understand how Eigrp actually works. You can check the values of how the values of these can be checked. I would also show that to you. Let me share my other screen with you. There you go. If you look into our topology, then I can show you. Do you see? I'll show you the topology table. There will be link failure over there. That's why there are so many messages. But show IP interface brief, or not show IP interface brief, show IP route. Oh, do show IP route. There you go. This particular value is called as FD. Okay, feasible distance. And if you check the topology table by running show IP Eigrp topology, then you can see for a specific route. There you go. This is the FD and that's the RD. You see, RD is lesser than the FD. RD will always be low than the FD. Make sense? You see, RD is low than, sorry, FD is greater than RD. So you will see both of these values into the topology table, and the route that actually has the lowest FD is going to be inserted into the routing table. Make sense to you? Do you understand that? If the feasible successor even goes down and then there is no route, then friends, there won't be any route there. You need to do the manual troubleshooting for that if there is no route. Okay. Then the third route will be advertised by the router in that case, and that particular route will become the successor in our case. Okay. Yeah. So that's exactly how EIGRP works. And that is actually all that we had to discuss in this particular class. So today we discussed about how RIP works and we discussed about how EIGRP works. In tomorrow's class, we'll be discussing about how OSPF works. Okay, and then we'll also see some switching methods as well. Good. So I hope you enjoyed today's class, and that was kind of a complex concept that we discussed today, but I hope I made it clear to you in the simplest way possible. I would request you guys to please go through the recording again before joining in tomorrow's class, so you'll have a better idea there. Okay. Yeah. So thank you so much for joining in. I wish you a good day ahead, and I'll see you guys tomorrow, same time then. Till then, take care of yourself. Bye bye. Thank you so much for joining.